What if one of the most fundamental rules we associate with life is wrong? We stand on Earth, a planet bathed in the energy of our star, the sun. Sunlight fuels the vast majority of life here, from the tallest redwood to the smallest plankton. This process, photosynthesis, seems like a non-negotiable requirement for a vibrant biosphere. But what if this is just a local ordinance, not a universal law? What if, in the cold, dark depths of our own solar system, an entirely different form of life is thriving? Powered not by light, but by the raw chemical energy seeping from a planet's core? This is the tantalizing question posed by Europa, Jupiter's enigmatic ice-covered moon. It forces us to confront a profound possibility that life can exist in total permanent darkness. So how could life possibly survive without the sun? The answer lies in a process with a deceptively simple name: chemosynthesis. It's life's other engine. Think of it like this: photosynthesis is a solar-powered factory, while chemosynthesis is a chemical-powered one. Instead of capturing photons, organisms capture high-energy molecules like hydrogen sulfide or methane that are released from geological sources. They then facilitate chemical reactions with these molecules, releasing energy in a controlled way. This captured energy is then used to do the same thing photosynthesis does: turn simple carbon compounds like carbon dioxide into the complex sugars that fuel life. On Earth, the organisms that perform this magic are called chemoautotrophs. Instead of a forest of trees, you have a dense mat of bacteria. These bacteria then become the food source for other, more complex organisms, like shrimp, crabs, and giant tube worms. On Europa, the same principle could apply. Its rocky seafloor, heated by the immense gravitational pull of Jupiter, could be leaking chemical reductants into the ocean. The oxidants might be supplied from the icy surface, where radiation from Jupiter splits water molecules into hydrogen and oxygen. To understand what life on Europa might look like, we don't need to invent fantastical creatures from scratch. We simply need to look down. Deep beneath our own planet's waves, in a place called the Midnight Zone, we find one of the most alien environments on Earth. Here along the mid-ocean ridges are hydrothermal vents, often called black smokers. These are towering chimney-like structures that spew out a scalding black plume of water and minerals from the Earth's crust. The water can reach temperatures of over 400 degrees Celsius, and it's laden with chemicals like hydrogen sulfide, methane, and iron. It is a toxic, high-pressure, and utterly dark world. And yet it is teeming with life. The sight is truly breathtaking. Giant tube worms, some over 2 meters long, stand in dense thickets. They have no mouth and no gut. Their bright red plumes act like gills, absorbing chemicals from the vent fluid. Inside their bodies they house symbiotic bacteria that perform chemosynthesis, providing all the nutrition the worms need. Swarms of pale, blind shrimp crawl over the chimneys, while ghostly white crabs scuttle between them. Mussels and clams cluster in thick beds, their shells filtering the water for the precious bacteria that sustain them. It is a complete, complex ecosystem, thriving in conditions that would be instantly fatal to most surface life. Europa is, on the surface, a desolate and inhospitable place. It's a world of ice, smaller than Earth's moon, with a surface temperature that plunges to a frigid -160 degrees Celsius. It's also bathed in the intense radiation of Jupiter's magnetosphere, a lethal environment for any life as we know it. But the magic of Europa lies beneath this hostile exterior. Decades of data from spacecraft have provided compelling evidence that this icy shell, estimated to be 15 to 25 kilometers thick, conceals a massive, globe-spanning ocean of liquid salt water. This isn't just a small pocket of water. It's an ocean that could be up to 100 kilometers deep and contain more than twice the amount of water in all of Earth's oceans combined. This vast dark ocean is kept liquid not by the sun, but by a different kind of warmth tidal heating. As Europa orbits Jupiter, the gas giant's immense gravity constantly tugs and flexes the moon's interior. This continuous stretching and squeezing generates enormous friction and heat, much like how a paperclip warms up if you bend it back and forth repeatedly. This internal energy is enough to maintain a liquid ocean and could even drive active geology on the seafloor, creating hydrothermal vents just like those found on Earth. This makes Europa's ocean one of the most promising places in the solar system to search for present-day life beyond our planet. The environment is extreme, but it possesses all the necessary ingredients for life as we understand it. First, there is liquid water, the universal solvent that facilitates the chemical reactions of life. Second, there is a potential energy source in the form of chemical gradients between the seafloor and the ocean. Third, there are the essential chemical elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the building blocks of life, and they are expected to be present in Europa's rocky mantle and ocean, just as they are on Earth. Searching for life on a world 600 million kilometers away, hidden beneath a thick shell of solid ice, is, honestly, one of the greatest challenges in modern science. We can't simply land a submarine and go for a swim. Instead, scientists must act as cosmic detectives, piecing together clues gathered from afar to build a case for habitability, and potentially, for life itself. The first step is to confirm the key ingredients. We need to be certain about the presence and properties of the ocean, understand the chemistry of the ice shell, and find evidence of an energy source. This involves using a suite of sophisticated instruments on orbiting spacecraft to measure everything from gravity fields to magnetic signatures. One of the most powerful tools in this hunt is spectroscopy. Every element and molecule absorbs and emits light at specific wavelengths, creating a unique fingerprint. By analyzing the light reflected from Europa's surface, scientists can identify the chemical compounds present in the ice. This is actually how they discovered that the reddish streaks are rich in salts, like magnesium sulfate, which is strong evidence that they originated from a salty ocean. Another key method involves studying Europa's magnetic field. Earth has a global magnetic field generated by its molten iron core. When NASA's Galileo spacecraft flew past Europa, its magnetometer detected a peculiar induced magnetic field. This field was best explained by the presence of a global conductive layer beneath the ice, a salty ocean. The way Europa's magnetic field changes as it moves through Jupiter's powerful magnetic field provides one of the strongest pieces of evidence for the ocean's existence, its saltiness, and even its depth. Perhaps the most exciting prospect is the potential to directly sample the ocean without ever landing. The hints of water vapor plumes erupting from Europa's surface offer a free sample delivery system. If a spacecraft could fly through one of these plumes, its instruments could directly analyze the composition of the ejected material. This would be a game changer, allowing us to taste the ocean's chemistry. We could search for salts, organic molecules, and even biosignatures, chemical traces that are indicative of life. The story of our exploration of Europa is a tale of tantalizing glimpses that have fueled decades of scientific curiosity. The first close-up images came from the Voyager probes in 1979, which revealed a surprisingly smooth surface. Unlike the heavily cratered moons of the outer solar system, it hinted at a young, active geology. But it was NASA's Galileo mission, which orbited Jupiter from 1995 to 2003, that truly revolutionized our view of this icy world. Galileo's detailed images showed the chaotic terrain of cracks, ridges, and rafts of ice that looked as if they had been broken apart and frozen back into place, much like sea ice in Earth's polar oceans. Galileo carried not just cameras but a suite of instruments that provided the most compelling evidence for the subsurface ocean. Its magnetometer, as mentioned, detected the induced magnetic field that screamed salty ocean. Its gravity measurements helped constrain the thickness of the ice and water layers. While Galileo was not designed to find life, it did something arguably more important. It identified Europa as a prime target in the search for it. Galileo's legacy is the reason why Europa is now at the forefront of astrobiology. Building on Galileo's legacy, a new era of Europa exploration is dawning. The flagship mission is NASA's Europa Clipper, which launched in 2024 and is scheduled to arrive in the Jupiter system in 2030. This is not a lander, but a sophisticated orbiter designed to perform dozens of close flybys of Europa. Its main goal is to investigate Europa's habitability by characterizing its ice shell, its ocean, its composition, and its geology. It will carry 9 advanced instruments, including high-resolution cameras, ice-penetrating radar, spectrometers, and a magnetometer far more sensitive than Galileo's. The ice-penetrating radar is particularly exciting, as it will be able to map the ice shell's thickness and potentially locate pockets of liquid water within the ice. The Europa Clipper's mission is to lay the groundwork for an even more ambitious future, a lander. While a lander is still in the conceptual phase, the data from Clipper would be essential for selecting a safe and scientifically interesting landing site. A lander could directly analyze the surface chemistry, drilling a few centimeters into the ice to get beneath the most radiation-damaged layer. It would search for organic molecules and potential biosignatures. The ultimate dream, of course, is a cryobot, a robotic probe that could melt its way through the entire ice shell and deploy a submersible to explore the dark alien ocean directly. This may be decades away, but it's a journey that begins with the vital reconnaissance of missions like the Europa Clipper. At a fundamental level, all life is about managing energy. Living things are complex, ordered systems, and maintaining that order in a universe that tends towards chaos requires a constant input of energy. On Earth, the vast majority of that energy budget is supplied by the sun. Photosynthesis is the brilliant biological invention that taps this stellar power source. Plants, algae, and some bacteria use pigments like chlorophyll to capture the energy from photons. They use this light energy to split water molecules and power a chemical factory that converts carbon dioxide into energy-rich sugars. This process releases oxygen as a byproduct, which has profoundly shaped our planet's atmosphere and the evolution of complex life. Chemosynthesis, the likely engine for life on Europa, follows the same fundamental principle but with a different power source. Instead of light energy, it harnesses chemical energy. It doesn't need chlorophyll. It needs enzymes that can manage the transfer of electrons between different chemical compounds. Imagine a battery. It has a positive and a negative terminal, and when you connect them, electrons flow, creating an electrical current that can do work. Chemosynthesis is the biological equivalent. It finds two chemicals in the environment. One that wants to give up electrons, a reductant like hydrogen sulfide, and one that wants to accept them, an oxidant like oxygen or sulfate. The key difference lies in the scale and location of these two processes. Photosynthesis is a surface phenomenon. It requires direct access to sunlight, limiting it to the tops of oceans and the surface of land. It painted our planet green and filled our atmosphere with oxygen. Chemosynthesis is a subsurface phenomenon. It thrives where geology and chemistry intersect, in places completely cut off from sunlight, like deep sea vents or potentially within the rocky, porous crust of a planet. It doesn't produce the same kind of global, atmospheric signature, making it much harder to detect from a distance. A world like Europa could have a thriving biosphere in its ocean, yet its surface could remain sterile and its atmosphere virtually non-existent. This comparison reveals a profound truth about the search for extraterrestrial life. We have long been biased by our own experience looking for Earth-like planets with sunlit surfaces, but Europa teaches us that the recipe for life might have more than one ingredient list. The search for life on Europa is more than just a scientific mission, it's a philosophical quest. It touches upon one of the most profound and ancient questions humanity has ever asked. Are we alone in the universe? For all of our history, we have known of only one example of life on Earth. Every organism, from a bacterium to a blue whale, shares a common ancestor. We are all part of a single, magnificent tree of life. This shared biology makes it impossible to know which of our traits are specific to Earth's history and which are universal requirements for life anywhere. Finding life on Europa would change that forever. If we were to discover life in Europa's ocean, and if we could determine that it arose independently from life on Earth, it would represent a second Genesis. It would mean that the origin of life is not an impossibly rare fluke, a 1 in a trillion shot that happened only here. It would imply that life is a natural, perhaps even common, outcome of planetary chemistry. The jump from non-living matter to a living organism would be revealed as a fundamental process of the cosmos, something that happens whenever the conditions are right. The universe would transform from a place that seems vast, empty, and sterile into one that is likely teeming with biology. This discovery would fundamentally alter our perception of our own place in the universe. Instead of seeing ourselves as the sole proprietors of life, we would become part of a larger cosmic community. It would be a moment of incredible humility and connection. The scientific and technological ramifications would be immense, opening up the new field of comparative biology and giving us insights into the fundamental nature of life itself. But the cultural impact would be even greater. It would be a discovery that would resonate with every human being, a piece of knowledge that would redefine our relationship with the cosmos. This is why scientists are so excited about Europa. This small moon orbiting Jupiter holds the potential to answer this grand question. The missions we send there, like the Europa Clipper, are not just gathering data about magnetic fields and ice composition. They are the first steps on a journey to find out if we have neighbors. Every piece of information, every image, every spectral reading brings us closer to knowing whether the spark of life has ignited elsewhere in our own cosmic backyard. Whether Europa's ocean is sterile or swarming with chemosynthetic organisms, the pursuit of an answer will teach us more about the conditions that make a world habitable, and ultimately, more about ourselves. The dark, cold ocean of Europa could be the place where humanity finally discovers it is not alone.